Hello students, and welcome back to Chemistry A. This is Ms. Sleight, and today we're going to be talking about waves, some of the calculations that we do with them, and how that relates to the electromagnetic spectrum. When we first talk about waves though, the first two things that we always look at are wavelength and frequency. Wavelength is just the distance from crest to crest or trough to trough on a wave, and we use units of meters to measure it. You can see in this image right here that they have marked the wavelength from the top of the first crest to the top of the second. Frequency is the number of waves that pass a point in a certain amount of time, and it's measured with units of hertz. So to get a better idea of what this looks like, let's look at this image. So the top one here represents a low frequency. There's only like two full waves in this time interval. But if we look at the bottom at the high frequency, we have 1, 2, 3, 4, 5, 6, 6.5 waves in this same time interval. So high frequency, more waves passing a point in an amount of time. In our lab from yesterday, we looked at what the relationship between wavelength and frequency was for a wave. And we got a graph that probably looked similar to what you see on the screen. And what we talked about this curve representing was the inverse function, because wavelength is inversely proportional to frequency. We can also represent this symbolically, like so. Now the first letter that you see up there, that kind of looks like a backwards H, that's the Greek letter lambda, and that is the symbol that is used to represent wavelength. On the other side, we have what looks like a V with a little curvy handle. That's the Greek letter nu, and it's the symbol that we will be using to represent frequency. Our equation that relates frequency and wavelength for light is C equals lambda times nu, where C is the speed of light in a vacuum, which is a constant 3.00 times 10 to the 8th meters per second. And again, lambda is our wavelength. It must have units of meters for this calculation to work correctly. And nu is our frequency in hertz. One thing to remember with hertz is that 1 hertz is the same as saying 1 over seconds. So we'll see how the units cancel when we do some example problems. So our first wave example problem says, what is the wavelength of a microwave with a frequency of 3.44 times 10 to the 9th hertz? Well, first off, anytime I look at a story problem, I like to circle the quantity that they want us to find and underline the given information. In this case, they want us to find wavelength, and they've given us frequency in hertz. Well, our equation that relates wavelength and frequency is C equals lambda times nu, where C is always a constant. I know that's going to be 3.00 times 10 to the 8th meters per second. And that equals my wavelength, lambda, times my frequency, 3.44 times 10 to the 9th hertz. Now that I have everything plugged in, it's time to do some solving. So I'm going to divide both sides of my equation by 3.44 times 10 to the 9th hertz so that I can get lambda, my wavelength, by itself. Since hertz is the same as 1 over seconds, hertz and seconds are going to cancel there. So now we just got to do a little bit of the calculation. When doing calculations with numbers in scientific notation, for division, the first thing we're going to do is divide the first two numbers like normal. 3 divided by 3.44. So that gives us 0.872 for 3 significant figures times 10. And then division, you're just going to subtract the exponents. So 8 minus 9 is -1. That's going to be units of meters. This isn't correct scientific notation, so we need to move our decimal one place to the right. So we're going to end up with 8.72 times 10. Actually, it's just going to be 8.72 meters. And that would be our final answer for what wavelength is. Let's look at another example. In example 2, we have green light has a wavelength of 4.90 times 10 to the negative 7th meters. What is the frequency of the green light? Well, this time, they're giving us wavelength, and they want us to find the frequency of the light. Again, we only have one equation that relates wavelength and frequency. That's C equals lambda times nu. Where again, C is our speed of light in a vacuum, 3.00 times 10 to the 8th meters per second. Take a moment to pause the video and see if you can finish this one on your own. All right, let's see how you did. So this time I know my wavelength, it's 4.90 times 10 to the negative 7th meters times my frequency. So I'm going to divide both sides of my equation by my wavelength to get frequency by itself. In this case, meters are going to cancel. Again, just like before, when doing calculations in scientific notation, we're going to divide the first two numbers like normal. And we get 0.612, three significant figures, times 10. Well, 8 minus negative 7, that's the same as saying 8 plus 7. So that is going to be 10 to the 15th, 1 over seconds, which we need to put in correct scientific notation. Move it back one. So we're going to have a final answer of 6.12 times 10 to the 16th hertz. Because remember, 1 over seconds is the same as hertz. Now let's talk about energy and frequency. The energy transferred by light comes in discrete amounts, little specific bundles of energy, you can think of it as. And it is directly proportional to the frequency of the light. Now we're going to talk about exactly why this is and kind of how we know that this is how energy and frequency behave when we do our experiment with the photoelectric effect. But for now, let's just go off the assumption that energy is directly proportional to the frequency of light. We can calculate this using an equation developed by Max Planck, and that is E equals h times nu, where E is your energy in joules, h is Planck's constant, which is 6.626 times 10 to the negative 34th joules times seconds. Again, don't worry about these constant numbers. They're not something you're going to need to memorize. The constants will always be given to you in problems. And again, nu is just your frequency in hertz. Now let's look at an example problem for calculating the energy of a wave. So our example 3 says a photon of violet light has a frequency of 7.23 times 10 to the negative 14th hertz. What is the energy of the photon? Well, if we are given frequency and we want energy, our equation should be E equals Planck's constant times nu. In this case, we're trying to find energy. Planck's constant is 6.626 times 10 to the negative 34th joules times seconds. Our frequency, they tell us, is 7.23 times 10 to the negative 14th hertz. This part should actually be a superscript in the question. Hertz and seconds are going to cancel. So at the very end, we will have just joules for our units of energy. Now we'll do our calculation. Again, when we are doing arithmetic with numbers in scientific notation, first thing, just multiply the first two numbers. 6.626 times 7.23. And we get 47.9, three significant figures, times 10. If we are multiplying, we can just add our exponents. Negative 34 plus negative 14 is going to be negative 48 joules. Now, this isn't correct scientific notation. We're going to need to move the decimal one spot, and this is going to become 4.79 times 10 to the negative 47th joules. Now let's talk about the electromagnetic spectrum. But to talk about electromagnetic spectrum, we also have to talk about electromagnetic or EM waves. An electromagnetic wave is a ripple in an electric or a magnetic field that's simply caused by a charged particle that's moving. And when you take a huge range of these waves and you arrange them, you get the electromagnetic spectrum. The electromagnetic spectrum is usually arranged in increasing frequency, and it's divided into 7 regions, which are radio waves, microwaves, infrared light, visible light, ultraviolet, X-rays, and gamma rays. Here's a picture of the electromagnetic spectrum. You can see here up at the top, they're listing wavelength in meters, and we start with longer wavelengths and go to shorter ones. At the bottom, you can see frequency and energy, where we start with lower frequency and energies and go to higher ones. In the middle here, you can see the 7 regions of the electromagnetic spectrum. Notice that visible light, the part that we can see of the spectrum, is just a very tiny sliver of all the electromagnetic waves that exist. You'll also notice that the categories kind of overlap with each other a little bit. And that's simply because this is a spectrum. There is a continuous range of things, so we can't make a true hard cutoff on anything. Also, down here in the middle, they also list sources of each of our types of waves. And the little pictures up at the top here give you a perspective for roughly how big this is. So radio waves can be like the size of a soccer field or a house. But if we're talking about X-rays and gamma rays, they're going to be like the size of molecules or smaller. And that wraps up our discussion of wave and wave calculations. Take care, and I'll see you next time.